Welcome to section 20.4 about Stokes Theorem. We're going to start by looking at the preliminary example where we will derive the statement of Stokes Theorem. So here's the situation. Imagine we have a surface S shown right here. Oops, different color. I want blue. So we have a surface S right here. And C is the boundary of S, oriented counterclockwise. So S is the whole surface and C is the outside. And it's oriented, so I'm going to draw it in blue right here. This is C. And it's oriented counterclockwise. And counterclockwise for us is going to be in this direction. And so the area vector of S would be pointing up. Now we are going to compute the line integral of a vector field F around C in two different ways. So the first way we are going to compute it is pretty much the normal way. So we have our curve C that goes around the outside of the surface S, and we have a vector field, and we are just going to compute the line integral. So we could do that. Now, what we can also do is imagine you are divvying up this patch into a bunch of subpatches, and you already see it right here. So I'm going to draw in these lines in green. And imagine computing a bunch of little line integrals around each patch. So for each patch here, you would get, for the first one, this would be your line integral. And then for the second one, this would be your line integral. So I'm going to draw in all my little arrows because, again, I'm going counterclockwise. And I do this for each of these little patches. And as I'm doing this, see if you notice something. What do you notice happening here? Almost done. So I'm going around counterclockwise for each little subpatch, each of these little boundary curves. And so I have all of those, right? I have all these little CIs right here. So each of my little green things is a little CI. So up here I have C1, and then I have C2, and so on. And so you see, if I computed little line integrals around all of these little curves C1, I get something. And then when I compute C2, the line integral around C2, I'm going against the direction that I went in when I computed the line integral around C1, and I get cancellation of this inside wall here, this inside boundary. And the same thing is going to happen when I go to C3. I'm going to cancel out what happened in the boundary between C1 and C2, and so on. So when I go in the next one, I'm going to get cancellation with that boundary, and you can see everywhere on each of these inside walls, once I'm going in one direction and once I'm going in the other direction. So all these little inside contributions to the line integrals are going to cancel out. And what I get is that when I sum up all those little line integrals, I end up with the same as the line integral just going around the outside. So I have that my line integral around C is the same as the sum of all the line integrals around the inside curves of F dr. And so let's say I goes from 1 to M, where M is the total number of patches that I have right here. Okay, well, this is pretty cool. I need, so let me write down a couple things that I didn't really say before. So SI is the ith surface patch. and CI is the curve around SI. And then I'm also going to draw, I said counterclockwise and I drew in counterclockwise, but that has to be with respect to some vector. And so my vector is pointing up right here to give me the right direction. And so this is my little area vector of the ith patch. So delta AI is the area vector of SI, and it gives me the direction of my line integrals as well. Okay, now what are we doing with this? Well, actually, it can be shown that this line integral on the ith patch is equal to the curl, of vector field F at some sample point pi on the ith little surface patch dotted with the area vector. And so I can replace that line integral around CI with this quantity. So I can say I have the sum not of little line integrals, but rather of the curl of F at pi dotted with delta AI. And now imagine, like we always do when we are integrating, taking smaller and smaller and smaller and smaller patches. So imagine taking the limit as n goes to infinity. Then this integral right here turns into a surface integral, into a flux integral. So that becomes the integral, the flux integral over S of the curl of F dotted with dA. And that is the statement of Stokes theorem. So let's write down Stokes theorem. So Stokes theorem says that if you have S, a smooth oriented surface with piecewise smooth oriented boundary C, and F, a smooth vector field in an open region containing both S and C, then the line integral around the boundary curve F, C of F dr, so this line integral, is equal to a flux integral through the surface inside of our curve C of the curl of F dA. That is a statement of Stokes theorem, the highlight of the end of the course. And so what is this good for? Well, note on the left-hand side of this statement, we have the integral over CF dr, and this is a line integral. And it's around the boundary of surface S. So on the left-hand side, we have a line integral. And on the right-hand side, we have a flux integral. We have integral over S, curl of F dA. That is a flux integral over the surface S. And so just like as we've seen before that we can replace one type of integral with another type of integral, either in Green's theorem or in the divergence theorem, now we have another formula, another theorem that lets us replace a line integral with a flux integral or vice versa. And so Stokes' theorem is mainly useful to replace a tedious line integral with an easier flux integral or vice versa. So sometimes you want to compute a line integral, but it's really bad. But the associated flux integral is easier to compute, and so we can just do that. Or sometimes you have a tricky flux integral, but the associated line integral is easier to compute, and so then we can compute that instead. And that's exactly what Stokes' theorem allows us to do.